have the slides that were at the end of the last presentation that weren't there. I was going to show you the one that I had corrected to show, yeah, I really did, but how do you know after the fact I didn't correct it afterward, right? So there's no way I can atone for that. This picture here is a picture showing the wave function and the psi mod squared for the simple harmonic oscillator. It looks quite similar really to what we saw for the particle in a box. The difference, of course, is a particle in a box has a firm wall rather than a wall that's changing. And you can see that now this line here is not very vertical. But the amount of the wave function that's outside of that straight wall that you'd have for a particle box is increasing as you go up to the higher states. The lowest state looks very similar, but as you go up, it's not. Also, this state here, notice you have a continuous wave function rather than the particle in the box. It actually is a sine wave, so it goes like that. So I said that there's normally a boundary condition that the slope has to be continuous. That's the first derivative of psi has to be continuous to the boundaries. But it was only because we had an infinite boundary that boundary condition wasn't required. And the beauty we get out of that is looking here at the probabilities, and you can see that the probabilities are still symmetric. So of course, the expectation value for position is going to be 0 in every state. But you can see that when you get to the higher states, it's not equally probable in these different positions. It's more probable being in the outer positions than it is being in the inner positions that are probability peaks. Okay, so I just wanted to look at the picture a little bit just to get some visualization of what our solutions are going to look like that we are going to find today. This is just reminding us what we've done. We started with the Schrodinger equation for a simple harmonic oscillator, writing the Hamiltonian, and then using the ladder operators as a substitute in the Hamiltonian. So the Hamiltonian we found can be written as h bar omega a minus a plus minus 1/2, or h slant omega a plus a minus plus 1/2. Now we only showed one of these. I don't remember which one we showed. Actually, did we show it? Yeah, we did.
Showed the top.
Okay. What was that?
We showed the first one.
Yeah. One thing that's important for us to do is to look at this commutator, to understand what that commutator is, because it provides for us to be able to directly go between those two. And it gives us good practice. You saw in your homework you have to find, 3 commutators? I'm guessing you looked at the homework, I don't know. So let's do that commutator. So what does it mean when I'm doing a commutator?
The first, it's so a minus times a plus minus a plus times a minus.
Okay, so what we're seeing is what's the difference if we change the order of the two operators. So these are operators here. I'm just not using any sign to indicate they're operators because we don't have any observable that goes with these. So now I'm going to have to substitute in our definition. And how do you evaluate any commutator? You always do something.
I'll multiply it by psi.
Yeah, you multiply it by psi. What's psi? No one knows, no one cares. But you multiply it by psi so you have something for the operators to operate on. So that's going to be a minus is 1 over square root 2 mh bar omega times a minus is plus I p operator plus, oh, crud. I can't remember. That's why I have this here, M omega X operator. So, no, it's M omega. I have M omega there. I'm going to stick with it. I think I did it right. So that's my A minus operator. My A plus operator is so there's my my first, and I have to have acting on psi. And then I'm going to have minus, and I'm just going to write it below. I'm going to copy and paste. It is nice to copy and paste, right? Oops, I want to keep that green. So that's a correct writing of it. The astute person probably would not have written it out the way I did, though. Why? Because we've already determined what the commutator is between P and X. So the astute person would have gone to a different way of doing this entirely. Now you might ask, why was I not astute when I started? Twofold. One is, yeah, I kind of forgot my preparation, right? It was at 5 this morning. I got an extra hour sleep. Yay. But number two is, it's kind of important to see the contrast rather than just see one way and say, did it have to be done that way? If I do it this way, I'm going to be doing a whole bunch of operations, seeing how it works together. But I could have also said, okay, let's recognize immediately that I can take those out. Every term is going to have that times that. So it's just going to have a 1 over 2 mh bar omega, not square rooted because I had the two of them. So I can write it like this, and then that gives me so there's my first one, the p hat with the p hat. And then I'll have so that's this one and this one. And then I'll have that is this one and this one. And finally, I'm going to change that to a parenthesis so it doesn't look like some kind of nested commutator, because you can't have nested commutators if you feel the need. By the way, I assume it's not snowing where you are, right?
Yeah.
It's kind of cool here looking out the window seeing the snow falling. Does it ever snow there?
It does every once in a while. It's nothing like that.
Yeah. Well, we don't have crazy snow. looking at these, which commutators can you immediately identify their values?
The person, yeah.
Yeah. What's commutator of P with P? Zero, because there's no difference in P operating on P and P operating on P.
Right.
So those two are real easy. The ones in the middle, we have minus x hat. Well, first we had positive p hat x hat, then minus x hat p hat. Changing the order is just going to change the sign. So these two together are just going to be 2, and I'm going to go this way, minus I m omega x hat p hat. But if you look in the textbook, or if you go back to where we did it, x hat p hat was I h bar. And so putting all of this together, there's the thing that was out front, and then the thing in parentheses is and then once again, we are all astute mathematicians here. We know that 2 and 2 cancel, and that m and m cancel, and h bar cancel, oops, and omega cancel. And we're left with minus I squared, and what's minus I squared equal to? 1. So that commutator is just equal to 1. So that means I could have taken this here and said, since that commutator is a minus a plus minus a plus a minus, then a minus a plus is equal to 1 plus a minus. And so if I just plug this in for that, I have 1 plus a minus 1/2 gives me, of course, 1 minus a half is a plus 1/2. And so it leads me directly to the second form. So we have two forms of the Hamiltonian. We like to stick with the upper one. Instead of leading you on a goose chase about why we like to stick with the upper one, I'll just cut right to the chase. The a plus and a minus are the raising and lowering operators. If you're in the ground state, A0, if you lower it below A0, below the lowest possible energy, what are you going to get? You're going to get 0. And so if you use this one here, this is correct. But if you have this operating on size 0, it's going to give you 0. It won't give you a wave function for that. And so we prefer the upper one. So now that we have this, our relationship between the operator and the wave function is our energy value, the eigenstate, and the operator. So there's energy value in the operator, or not in the operator, energy value in the wave function. Now, this is what I started to show you. Remember, I didn't have the slide, so I was then trying to remember what was the next thing I did, and this was what I was starting to do at the end of last class period. So now that I've laid my foundation, let's go ahead and do this carefully, not forgetting to put the not dropping one of the A pluses. And I'm going to use color coding this time so I don't confuse. Okay, so there I've replaced the Hamiltonian with the Hamiltonian using the raising and lowering operators. And I chose the form that had the A plus A minus, so that the second one is the opposite as what I had in my psi. Following through with my math, this is so there I have simply shifted the A plus from operating directly on the psi end to being at the tail end of the operators that were present. Now, constants, the operators can freely move past a constant. And so now I'm going to rewrite this once again. Now, here, I'll change this color just to make it clear. I had to break down on my color coordination because this A plus out front is this one and this one. They're different colors. So now I take this and I say, well, what do we have here? This here, based on the commutator we just did, we had A minus A plus is equal to 1 plus A minus. Right, that's this here. And so taking, see, did I get all my signs right? A minus A plus is 1 plus A minus. Yeah. And so taking this, I could write this as okay, what I did here is I just took the 1 out. So this 1 was moved out there to a separate term. And now we see our great aha moment. That right there is our Hamiltonian. And so that's equal to E sub n. And so I'm left with and that gives us our final, yeah, just making sure that is what I'm looking for. Now I just move the A plus back over to the psi n, since everything's now a constant. So we see that indeed, if I have my Hamiltonian operating on a plus psi, that gives me a value here times that same function, a plus psi, which indicates that a plus psi must also be a solution to the Hamiltonian. So now we have, it's a solution that raised the energy. A plus, we deduce, must be an energy raising operator, hence our term ladder operator. It raised the energy. And analogously, I could have shown that if I did the negative, it takes it down to a lower energy. So we conclude then that the energy levels have a ground state energy of 1/2 h bar omega, and for each n, each possible energy state, it's just n plus 1/2 times h bar omega. So basically, this is really simple. The energy states are 1/2 h bar omega, 3/2 h bar omega, 5/2 h bar omega, and so on. So usually, we're pretty satisfied to get to there. We feel pretty good. We've now found the energy states, and we didn't actually have to do any real calculus, not really even much algebra. It just had to use a stupid trick and a whole bunch of commutators. I say stupid trick, an arcane trick. Well, we do like to have wave functions as much as we can. And so we're going to find the wave function now. So we take the lowering operator on psi 0, that's if we're on the ground state, and we try to lower it from the ground state, we just get 0 because there is no state below the ground state. The textbook gives us two options, but that's the one that occurs. So the lowering operator on the ground state is 0. So here I wrote out the lowering operator acting on the ground state is equal to 0. And then substituting, well, first, notice that I just multiplied everything by square root of 2h bar m omega. Because why not? It's equal to 0. Let's get rid of the constant out front. And then I substituted in what the momentum operator is, so minus I h bar ddx. And we have ourselves a first order differential equation. And this is one that I'm sure, being a month into the semester almost, you can solve. So as a tag team, go ahead and lead through how we're going to solve that. So I'm going to rewrite this. Notice I times minus I is 1, just like we've already seen. I'm going to divide everything by h bar, so I'm going to have d psi 0 dx is equal to minus m omega over h bar x psi 0. How can I solve this for psi 0, gentlemen? I know the class would go much quicker if I just told you the answer, but well, it's important to understand how we got there, so when you do harder problems, you can do them. Right? We're not doing these for the answers. We're doing them so we understand how you get there.
That's x is in the variable, not
X and psi are variables, yeah.
okay.
I mean, psi is a function of x, but as far as we're concerned in the derivation, it's just a variable.
So you just integrate, right?
Well, first you have to separate variables. So what is my step going to be to separate the variables?
You're gonna multiply by the dx, and then you're gonna bring the psi over to the side.
Yep.
Yes, so the 1 over psi 0 is equal times d psi 0 is equal to other stuff.
Is equal to other stuff. Absolutely right. Now the left side is independent of the right side. And I know it sounds a little mushy since psi is a function of x, but they're independent. And so now we just independently integrate each side, and we get natural log of psi 0 is equal to, I always want to put that early, minus m omega over 2 h bar x squared. It's pretty obvious, but where did the 2 come from?
The 1/2.
Yeah, the 1/2 x squared, exactly. And then our final step, how do I get rid of the natural log?
You raise both sides.
Both sides to E.
Raise both sides.
Including C or not?
Are we including C? No, we're not. No, we're not. We could write this different ways to make it feel better, but no. So we have psi 0 is equal to there's one thing missing on this. And that one thing is what would have come about if we'd put the constant in. We put plus C.
So a C in front of the E's and stuff.
Yeah.
Or like a constant is
Yeah, if I put plus C here, then I would have had times E raised to the C, which I'll just call A0.
Does that translate to your normalization constant?
That's exactly, yeah. It has to be normalized, so that constant is going to be dictated by it has to be normalized. And so guess what we're doing next? We're going to normalize this beast. Did anybody happen to bring the Gaussian integral table? No?
I have my phone.
Yeah, actually.
E class on it.
So since Chris has his computer, that's bound to be the quicker solution, I think.
I'm there. Exactly.
I'm wrong. And he was faster. Okay, what is our normalization method? Right, asking you these questions just to keep you on your toes.
Okay, so it's
1 equals the integral.
Hey, fine.
E to your wave function. Your wave, your psi star times psi dx.
And
From
because this is not a particle in a box, the wave function exists everywhere. And so it's from minus infinity to plus infinity. Now we'll make the substitution that you were starting to say. A0 star e to the minus m omega over 2h bar x squared times A0 e to the minus m omega over 2h bar x squared dx. A0 mod squared, integral from minus infinity to infinity of e to the minus m omega over, notice it was over 2, but I have this thing squared, so the over 2, when you add the 2 exponents, disappears. And so we need to look up this integral.
So if all the stuff in front, if the m omega over h bar is a,
Yes.
this integral is going to be, so it isn't even, yeah, it isn't even. So it's
Good thinking, by the way. One of the homework problems, that's how you're solving it, even versus odd integrals. It tells you not to evaluate the integrals to try to hint at that.
Okay, so then from the integral from 0 to infinity is 1/2 the square root of pi over a. So then it would be 2 times 1/2 the square root of pi over m omega h bar. So h bar pi over infinity.
So I put the 2 out front like a genius. Obviously, 2 and 1/2 works out nicely. And so what is a mod squared equal to?
So it's going to be it's gonna be m omega over h bar pi all to the 1/4. Oh, sorry, 1/2 power, and then you'll take a square root.
Right. You're just going the step ahead to the answer. So if we want without the mod squared, oh, perfect. Then it's going to be to the 1/4. And so there's my A0. So now we have ourselves a normalized wave function. We did have to do some calculus in the end, but we got there by using the ladder operators. Now let's check to see what the energy is from this wave function. So our wave function is, here's the work that we just did. In case none of us had the integral table, I had the important integral here. So we have this and this. So let's go ahead and just find what is the energy. So, and let's even do it a little more sophisticated. What's the kinetic energy and what's the potential energy? Notice I shift between partials and exact derivatives. I did the exact before, now I did partial. The partial is for if you have x, y, and z, or x and t, or, you know. But I need to do that second derivative. So first I'll do the first derivative in gory detail. Now, why do I have minus m omega? Oh, why did I forget the last part? Okay, why do I have minus m omega x over h bar?
Because of the chain rule.
Okay, works for me. You got to bring down the derivative of the exponent. And did I do that right? There was a 2 there, so yes, I did. Right. So now we take the second derivative. Okay, now, since I worked a little quickly, did I do that right? Yeah. Pretty sure that's right. Except for one thing, there's an X right there. I think, did I make more mistakes, or were you laughing because you had seen that already?
No, we were just talking. I was telling them, isn't there supposed to be an X? And then right after I said that, one thing, there's supposed to be an X. Yeah.
All right. That appears to be correct for me. So that's my energy. My energy is dependent on the position here. Depending on the position, the single X? No, of course not. It's an X squared because when I did this, the second, there's an X that comes out of the derivative as well. All right. So this here is my psi 0 again. And if I bring these things together, it's my spacing is fine here. So this is what I got from my kinetic energy. My potential energy is going to be plus this, so I guess it makes sense. So the total energy is h bar omega over 2. Right, because the potential energy is the easy one. I swear I tried to change colors, but I hit the same color every time. So that's the potential energy. This here is the kinetic energy. And so the energy total is the sum of those two, which is just going to be the h bar omega over 2. So now we took it kind of on faith that the ground state was the lowest positive energy state we would get with the lowering by h bar omega every time. But now we see that from our calculation of what the wave function is, the operator gives us that ground state energy. So it gives me a little more confidence in that ground state energy. As you can see, there's always a bit of trepidation for me when I'm doing all this long math because, you know, like I forgot that extra X once. That would have made a big difference, right? Yeah. So we have a normalized wave function. We verified the ground state energy. What else can we do with this? There are a few more things we can do with this, like finding another wave function. Screen's dimming. That means the battery's getting low. It's okay. We only have 10 minutes. We'll make it. So we can find other energy states by using the raising and lowering operators. So how so? This relationship here, for any energy state psi sub n, the Hamiltonian acting on psi sub n needs to be the energy acting on psi sub n. But the energy acting on psi sub n is h bar omega n plus 1/2. So that means that this thing here is going to have to give me n plus 1/2. Which means that the a plus a minus had better equal n. Or And this here, because it has a minus 1/2, then the A minus A plus, it better be one higher than that. So we have eigenvalues for A plus, A minus, and A minus, A plus. So those are going to help us in finding what our wave functions, all of our different wave functions are. And here's how. If I want to go to the nth wave function, I'm going to have some normalization constant A sub n, which right now we're remaining like, I don't know what it is. And then I'm just going to do the A plus operator to the nth power, right? I'll do it n number of times operating with A plus to raise it to the nth state. So in your homework problem, you have to find the fourth state for n equals 4, which may be going a little far. You're finding the Hermite polynomials, by the way, in case you want to check your answer. I'm sure you can just look up and what is the fourth, but I want you to show going through the steps to build yourself up. So here is an example of doing the psi 1. And the textbook does show, I think, the wave functions up to 3 or something. That was actually why I chose 4. I was thinking that it showed up to 3. So here it's actually showing, notice it's just gone to the regular definition of the A plus. And so you do that operation on the psi, and it gives you this function. Okay, that wasn't so bad. Is it normalized? No. No, I say it wasn't so bad. I obviously didn't do the math, but it wasn't that hard. You had to take one derivative. How hard is one derivative? We already did essentially that work. So it's not normalized. So now we have, oh, yeah. Is it normal? You could have seen the next slide was normalizing it. So how do we normalize it? And this is bringing in a new area to understand. Something that's important about the Hermitian operators is this relationship here. I have a function star, right, complex conjugate, and then I have an operator. This right here is equal to, well, got to get the star inside, is equal to that. So if you take the A plus and have the A plus act on the F, and then you do the complex conjugate of the whole thing, that's the same as having the A plus after it. Now, you're asking, or you should be asking, well, how is that really going to help me? It is going to help us when we learn how to do things like with the Dirac notation, which I hope is coming soon because I want to be able to shorten my writing time. Have you guys seen Dirac notation in another class in your modern physics? Also known as Bra-Ket notation.
I've seen it a little bit in electrodynamics.
Okay, well, I'm going to show it to you right now. If I do this, that's ket psi. That's how we say it, ket psi. And what that means, well, technically you go like this, and, well, technically this is psi of x. We often think of the ket psi as psi of x, but technically bra x is how we say that, is this. And when you close them, it implies an integral. So I'm going to write it this way. this implies the integral of psi star psi, and I'm going to put dx. It doesn't have to be dx because this here is technically that, but you could have put like psi in terms of a different variable besides x. But when you see the bra and the ket together, it's an implied integration. Now, you can see that that's shorter to write. And then we have things like our eigenvalue, eigenfunction relations are written like that. And expectation value of h is like that. And so this notation is very powerful in that it allows you to write things in an easier fashion. And so, yeah, it's just because it's so much easier to write this type of relationship as right, that's writing the relationship in bracket notation. Okay, so that's why I was thinking about it now. All right, so how is that going to play out for us using that relationship? Start with the relationship that A plus is equal to some normalization constant. A plus acting on psi n is equal to some normalization constant times psi n plus 1. So it gives me a new normalized state. Putting that in for both, I'm going to have A plus psi star, right? So this is here and here. And this has to be 1 if it's going to be normalized. But then using the relationship from above, I'm going to take this and put its complex conjugate in front of the A plus psi n. Has to be in front. The order is important. But the complex conjugate of A plus is A minus, because the difference in A plus and A minus was the sign in front of I. But now this is A minus A plus psi n, psi n. This here we know is going to be normalized, and A minus A plus acting on psi n is going to be n plus 1. So we have n plus 1 times 1 is equal to 1. Whoops. That's not equal to 1. It's equal to Cn mod squared. Did I do that right? I'm thinking really clearly suddenly. I want to show that psi n plus 1 has a, shall we say, an expectation value of 1. Right, it's normalized. And so if psi n plus 1 is equal to this stuff over Cn, then this stuff mod squared should be 1 over, no, that's equal to Cn mod squared. And so that's going to give me my normalization constant. I have Cn mod squared is n plus 1. So here's the result of the one we just muddled through, that the Cn plus, or Cn is equal to square root of n plus 1. And then this here is doing it with minuses, which gives you a plus a minus, so you have square root n. And so that allows you to build, this is what you're doing in the homework problem then. To build your fourth wave function, you're going to have 1 over n factorial, so 1 over 4 factorial, that's 1 times 2 times 3 times 4. And then you're going to have to do that raising operator 4 times on size 0. And so that is a number of derivatives. And now I went over time. Probably would have kept it in time if I had been more concise in this line and not gone through the bracket notation. Yeah, we'll start the analytical method Wednesday. I don't know if you guys have school on Friday. I know that Indy's going to be gone on Friday, and we don't have school on Friday, so I was not even planning class on Friday anyhow. So do you guys have school on Friday?
Yeah, I think we do.
Okay.